Okay, we're on section 3.2, Gibbs free energy. You have to bear with me while I try and make this so you can see the book and me at the same time. In the warm-up, it says to write a balanced chemical equation, including phase subscripts for the reaction shown in the diagram. So inside of the balloon, we've got 2 hydrogen gas molecules and 1 oxygen gas molecule. So for a balanced equation in number 1, you've got 2 H2 gas combining with 1 O2 gas, and then you're going to produce 2 water molecules. They come out on the product side, and those are also in the gas phase. It says use the values in table A8 in the appendix at the back of this book to calculate delta H and delta S for this reaction. Okay, so what we're going to do is we're going to use, I'll write these over here. We're going to use the values in the back of the book for our delta H. So this is going to end up being the product minus the sum of the reactants. So since I've got a 2 in front of the H2O, this is going to be 2 times 241.82 for the water. And then we're going to subtract the reactants. So our hydrogen is 0. So it's 2 times 0 because of the coefficient of 1 in front of the H2. Plus we've got 1 oxygen, and that is also a value of 0. So this is going to end up being negative 483.64 kilojoules per mole for our delta H. And then for your delta S, using the values in the back of the book, this is 2 times 188.83 for our H2O minus 2 times 130.68 plus 205.14 for the oxygen, and then this is going to end up being negative 88.84 kilojoules per mole. Now, the third question is, what is the function of the candle in this process? So that is helping us overcome the activation energy. So that's providing enough energy to get those reactants to convert into product. Number 4, is the spontaneous process enthalpy driven or entropy driven? Explain. Well, we've got a negative delta H and a negative delta S. So this negative delta S is implying that our entropy is actually decreasing. So this would actually be an enthalpy driven process. If you take a look underneath the quick check, or I'm sorry, the warm up rather, you will see that we've looked at 2 factors now, enthalpy and entropy, to determine whether or not a reaction is spontaneous or thermodynamically favorable. And when the enthalpy and entropy oppose each other, the overall reaction spontaneity is less obvious. So the net effect of the 2 factors can be determined through another quantity called Gibbs free energy. Gibbs free energy is abbreviated with a capital G. In order to determine Gibbs free energy, you take the enthalpy, the change in enthalpy for that process, minus the temperature in Kelvin times the difference in entropy for the process. Now, if you look onto the next page, at the top of the next page, they show us that a change is spontaneous only if it is accompanied by a decrease in free energy. So that means the delta G has to be negative in order for a spontaneous process to occur. Spontaneous processes are also termed thermodynamically favorable changes, okay? So if you take a look down at the table, it is very important that you know all of the different scenarios for whether delta S is positive, negative, and then the corresponding delta H, and how that plays a role in determining our delta G. So you're going to want to basically memorize this table. And because You will see multiple choice questions related to it, whether it's on an AP exam or one of my tests. And you also need to know the reaction characteristics that are in the table as well. If you come down here, reactions that occur with a free energy decrease are termed exergonic. Those that have a free energy increase are endergonic. If you take a look at the next page, let's turn to free energy and maximum work, which is here. You can't take all of the energy that's released from some sort of a spontaneous chemical process and like grab it all, harness it all, and use it. So some of the energy is actually going to be lost as heat. And the maximum amount of energy that we can actually harness from a reaction as work is delta G, or the change in Gibbs free energy. So this is energy that's not lost as heat, and it's free, or it's available for us to use as work. So if you take a look under free energy and equilibrium, reactions that have negative free energy changes are spontaneous or thermodynamically favorable. Those that are positive free energy changes are non-spontaneous. If your delta G value is 0, then that means that we are at equilibrium. And if we set our delta G equal to 0, and that equals our delta H minus T times delta S, we can rearrange this equation to solve for delta S. And that gives you delta S of the system is equal to delta H over T. Let's come down here to the quick check. It says for the process, liquid bromine converting to bromine gas has a positive delta H and a positive delta S. Explain why a positive value for the enthalpy change is reasonable for this process. Well, vaporizing requires heat energy. And it's endothermic. So it makes sense that we have a positive delta H here. B, why would we expect entropy change to be positive for this process? Well, when you're converting to the gas phase, there are going to be more microstates. There's more positions of variability. There's more places in space that they can occupy. So that's why you've got this positive delta S. C, assuming delta H and delta S are temperature independent, calculate the temperature at which bromine will be in equilibrium with, liquid bromine will be in equilibrium with bromine gas. Give the answer in degrees Celsius. So for C, your temperature is going to be equal to delta H divided by delta S. So this would be, I'm going to convert, since we've got 31.0 kilojoules per mole, we should probably convert kilojoules to joules. And then on the bottom, we've got our 92.9 joules. And now our joules match, so our units match, so they can cancel. You're going to end up with 334 Kelvin. Just subtract 273 from this to get 60 degrees Celsius. Then you've got D. D says, what property does this temperature represent for bromine? This is going to be the boiling point for bromine, okay? Look on the next page at standard free energies. So Gibbs derived the free energy equations, and Helmholtz deduced the same thing. So we have this equation called the Gibbs-Hemholtz equation, which is referring to the delta G equals delta H minus T times delta S. And we're going to start looking at calculations for standard conditions. And standard conditions are where our pressure is 1 atmosphere and our concentration, if it applies, would be 1 molarity. And when we do that, you're going to notice that they're going to place little degree symbols in the upper right-hand corner for the delta G and the delta H into that equation. So that represents your standard conditions. As we go down a little bit further, the standard delta G values are available in the back of the book. And so are the standard delta H values and some standard delta S values. The difference, if you take a look at this graph here, the difference between enthalpy and free energy is actually equal to T times S. So that would be the temperature in Kelvin times entropy. You will notice that as the temperature increases, the difference between the two forms of energy becomes larger. Now, since enthalpy and entropy are state functions, and you should definitely know what is a state function and what wouldn't be, state functions, enthalpy, entropy, and Gibbs free energy, it doesn't matter the path that I use to get that value or to get there, those would be state functions. And so we can use the reference values in the back of the book to calculate them. And note that the standard delta G for an element in its normal state, meaning is it normally a gas, is it normally a solid, at 25 degrees Celsius in 1 atmosphere is equal to 0. And that is available right here underneath as a definition underneath how to calculate delta G. So we're going to use the same process that we used in another section for calculating delta S and delta H using the reference values in the back of the book. If you take a look at the practice problems here, practice problems 3.2.1. So here it says that use the standard delta G values in table A8 in the appendix to calculate delta G for the combustion of ethanol under SATP conditions. Okay, so here we need to write out our balanced chemical equation. This is going to be ethanol, which is CH3CH2OH, plus oxygen. When it's balanced, there's a 2 in front of it, plus 2 carbon dioxide and 3 water vapor. So I'm putting the states of matter in here so that you can use that when you go to look up the standard values. So this is going to be 2 times negative 394.36 for my carbon dioxide, plus 3 for my water times negative 228.57. So that's the sum of the products minus the reactants, which is going to be negative 174.78. And the oxygen is 3 times 0. So this is going to come out to be negative 1299.65 kilojoules per mole for that reaction. Okay. All right, now let's take a look at question number 2. Question number 2 says calculate the maximum work available from the oxidation of 1 mole of octane at 25 degrees Celsius in 1 atmosphere. Use the delta H and the standard entropy values from table A8 in the appendix, along with the Gibbs-Hemholtz equation. Okay. So here, we're going to take octane. So this is going to be 2C8H18. And this is a liquid plus 25 oxygen gas is going to form 16 carbon dioxide gas plus 18 water vapor. My delta H values are going to come from the back of the book. So 16 times negative 393 for my CO2 plus 18 times negative 241.82 for my water. And then we've got minus 2 times negative 5471 for the octane plus 25 times 0 for the oxygen gas. So this means my delta H is going to be around 293.08 kilojoules per mole. And I may have used, it looks like, my water. I might have used liquid water here instead of water vapor, I think. Now down here, my delta S is going to be 16 times 213.74 plus 18 times 188.83 for the water, and then minus 2 times 358 for the octane, plus 25 times 205 for the oxygen. So that means your delta S is going to be around 974.28. Okay. Now, they want us to use the Gibbs-Hemholtz equation. So that means you're going to use this delta H value and this delta S value inside of it. So let me use black because it'll probably show up better. So here my delta G is equal to delta H minus T times delta S. And my delta H was 293. And then my temperature is 298 Kelvin. And my delta S is 974.28. So here you're going to end up with negative 290 kilojoules per mole. Spontaneous process because my delta G is negative. Okay. Now, let's take a look at calculation of free energy at non-standard states. So standard Gibbs free energy is the most temperature dependent of all of the thermodynamic functions. And standard enthalpy changes are pretty much independent of temperature. And the variations of standard entropy change with temperature are pretty small. So entropy is mostly dependent on temperature near absolute zero. And near room temperature variations in entropy, standard entropy changes are pretty much minimal or negligible, not really relevant because they're so small. If you take a look at the next page, I went a little too far, go to the practice problems. I want to look at practice problem section 3.2.2. So this is where we're dealing with the Gibbs-Hemholtz equation at non-standard temperatures. So here it says that we've got the mineral calcite decomposing. We've got our delta H and our delta S. Note that your delta H has kilojoules per mole. Your delta S has joules per mole. You've got to make sure that your units match. I'm going to convert this delta S to kilojoules by just moving the decimal. So it's 0.1606 kilojoules per mole times Kelvin. And then if we're going to calculate our delta G, we're going to use our delta H minus T delta S. So this will be 178.3 for delta H minus. Your temperature is 750 degrees Celsius, add 273 to get that into Kelvin. That's 1023 Kelvin times 0.1606. And this is going to end up being 14 kilojoules per mole times Kelvin. And then part B says calculate delta G at 950 degrees Celsius. Okay, so if we're going to do that, that means that this is going to be equal to 178.3 minus 1223 Kelvin times 0.1606. So this would be negative 18.1 kilojoules per mole. So now, C says, does the reaction become more or less spontaneous as the temperature increases? Well, as the temperature increased, it became more spontaneous because now my delta G is negative. Okay, last part of the section. Under the experimental manipulation of the Gibbs-Hemholtz free energy equation, it says you can rearrange the equation into a different form. And if they plot Gibbs free energy versus temperature, you get a straight line with a slope of negative S and a y-intercept of H. Okay. So here this shows how free energy varies with temperature. Since all substances have a positive value for entropy, G is decreasing as temperature increases. And gases have the greatest entropy as opposed to solids, which would have the lowest entropy. And this figure shows us that free energies of gases are more temperature dependent than liquids, which are more temperature sensitive than solids. And that has to do with how steep these lines are in the graph.